Good afternoon, students. Today we have to see design of armature related things. First we have to see some theoretical expressions. After that we can go for the related problems. Armature design, it includes the design of windings. First one, very beginning. The windings used in synchronous machines may be single layer or double layer type. Machines are having larger flux per pole. It results smaller number of turns per phase. Hence, at this condition, the double layer windings are suitable. However, for high voltage machines with smaller values of flux per pole, then automatically it has larger values of number of turns per phase. At this situation, multi-turn used. Again, there is a option, there is a choice. We can select double layer lap winding, either we can select single layer concentric type winding. In modern practice, a double layer wave or lap winding is used. The coil span for windings are chosen such that harmonics are to be reduced. We are already knowing the main effect of harmonics due to fifth order harmonics as well as seventh order harmonics, which affects on performance of the machine. Hence, the maximum reduction of these harmonics by using a coil span of 8.33% of pole pitch, or in other design practice, the pole pitch, it is the ratio of number of slots to the number of poles is used in general to decide the coil span, or it is nearer, how much value is nearer to this one you can use as per the design considerations. Very important part of this concept is this number of armature slots. Number of armature slots. It has been asked number of times in VTU examination for 8 to 10 marks. List the factors effects on the choice of armature slots in three-phase synchronous machine and discuss each one. A very important part. You concentrate and practice. First you make the factors. For example, the factors effects on the choice of armature slots are balanced winding, cost, hotspot temperature, leakage reactance. Just like you go on list, this list only carries 2 marks. After that you can go on discussing each one only for few points. For example, number 1, balanced winding. The number of armature slots should be selected in such that it should have a balanced winding in the machine. Otherwise, in some cases, in some generators have also designed with unbalanced armature winding. It is not creates so much illness on the performance. Hence, it may be also used, but the use of unbalanced winding results, overheating of the rotor surface due to space harmonics or excessive triple frequency currents flows through the neutral. You remember, choice of armature slots results balanced winding. Point number 1. Point number 2, cost. The selection of armature slots will also affect on the cost of machine in usual practice. Hence, we have to select smaller number of armature slots, which may result economical design, because if we are using the less number of slots, number of coils, that is requirement of winding material, copper, it is also required less amount, and insulation required for the respective coil is also less, and automatically it becomes less cost. Hence, cost is also one of the major factor. Third one, hotspot temperature. If a small number of slots results bunching of the conductors, that means conductors are placed very close to each other. Hence, a less space is available for circulation of air, which may results a development of high internal temperature in the conductor, that should be referred as hotspot temperature. when it is possible if we are using less number of slots. Slots are to be selected in such a manner there is effect of hotspot temperature should be less. Hence, we have to go for high values of selection of number of armature slots. Then leakage reactance, it is also one of the important factor. The selection of number of armature slots will also affect on the leakage reactance of the machine. Leakage reactance affects several cases. Hence, selection of number of slots will give rise to less leakage reactance. If we are using the less number of slots, then less leakage reactance, because the leakage flux and leakage reactance is increased due to conductors are lying to near each other. Hence, this is the option. More number of slots are used. More number of slots are used, then more conductors are lying nearer to that. Hence, leakage reactance is more in the case of when the number of armature slots are high, then you should select such a value. Next point, tooth ripples. It is also one of the major factor. The tooth ripples in the field and consequent pulsation losses of the pole face decreases if we are using larger number of slots. It is also one of the choice. If we are using the larger number of slots, the loss, tooth ripple loss also reduces. Also, the waveform of generated voltage free from ripples, it is another factor. Flux density in the iron. With larger number of slots, a greater space is taken for insulation, hence which results in narrow teeth. A narrow teeth carries higher flux density. It may be beyond the acceptable limits, hence tooth becomes mechanically weak, and flux density in the tooth is also designed under the safe limit. It should not cross beyond acceptable limits. Hence, this is also one of the important factor for the flux density in iron. Next one, slot pitch. The value of the slot pitch is depends on voltage rating of the machine. The value of slot pitch depends upon voltage rating of the machine. For example, for 25 mm slot pitch, we can go for low voltage rating machines. Slot pitch 40 mm, it may be for 6 kV, or still it may be voltage rating less, or highest slot pitch may be 60 mm for machines up to 15 kV. Hence, slot pitch is used depending upon voltage rating of machine. Next important design part, turns per phase. Armature turns per phase. We know that flux per pole phi equal to B average into tau into L. From this expression, you can write the expression, or you can estimate turns per phase Tp equal to EP divided by 4.44 F phi kW, where EP is phase voltage, flux per pole is phi, kW is stator winding factor. This above expression, if number of parallel path is 1, if number of parallel paths are more, for example, A be the number of parallel paths, then equation 2 represents Tp equal to EP into number of parallel paths divided by that same expression. Then continuation of that, armature conductors, design of armature conductors, current in each conductor Iz equal to Ip when number of parallel path equal to 1, or design of phase current for number of parallel path equal to 1, that is kVA rating of machine into 3 times of phase voltage, where we are going to get phase current. If number of parallel paths are more, for example, you select A be the number of parallel paths, then current in each conductor equal to phase current divided by number of parallel paths, that should be equal to phase current IP divided by A. A is the number of parallel paths. For normally cooled machines, permissible current density may be considered as 3 to 5 amperes per millimeter square. Once you are assuming selecting some current density, then you can easily estimate area of cross sectional area of armature conductor, that is current flowing through each conductor divided by current density of respective. Then next we can go for slot dimensions. The flux density in teeth at no load, it should not be more than 1.7 to 1 Webers per meter square. Hence it is possible to design minimum width of tooth, that is WTR minimum equal to phi divided by xi divided by S by P Li into 1.8. For parallel slided slots are used, therefore teeth are tapered. Combination, we are knowing the combination. If we are using the parallel sided slots, teeth are tapered. Their minimum width occurs at the air gap surface. Hence maximum width of slot, that should be equal to WT maximum equal to slot pitch minus of WT minimum. Next, another important factor we have to design LG, length of mean turn, length of air gap. That length of mean turn LMT equal to 2L plus 2 tau plus 0.06 kV plus 0.2, where kV is voltage rating of machine in kilovolts. A stator core, the value of depth of core, that is the abbreviated DC, it may be calculated by assuming suitable value of flux density in core, that is referred as BC. The value of flux density in the armature core for salient pole machine lies between 1 to 1.2 Webers per meter square. Hence depth of armature core DC equal to, use the expression, then outer diameter of stator D naught equal to D stator bore diameter plus depth of stator core, depth of stator plus depth of core, that is 2 times, ds in circumference, depth of slots comes 2, depth of core comes 2, hence d plus 2 times of this value, it gives outer diameter of stator d naught. If you draw the circle, you get the 2 times width of slots, 2 times width of depth of core.